Are there any questions about anything we talked about before lunch? Does anybody remember anything we talked about before lunch?
No.
The setter example that you have, you will discuss later how that should...
We'll discuss that later.
Good.
We're coming to that. Now, I have noticed that we are progressing through the material somewhat more slowly than I had expected, which is fine for me. I like it when I get questions. The only reason for coming to a seminar, in my view, is you get to ask questions, otherwise you might as well read books. However, we are supposed to stop at 4 o'clock today. I am happy to go later than 4 o'clock, but what I need you to do is, if you need to leave at 4 o'clock today, come and tell me, please, at the next pause, so I can try to figure out what to do about that, because I can cover all the material, but I want to talk really fast like this, and it's probably not very good for you guys. So we don't want to do that. So if you need to leave at 4 o'clock, let me know, and we'll work something out. But I want to get back to universal references versus rvalue references. And what I had explained immediately before lunch was that although this function is in a template, and even though the parameter is a tref, which is the proper form, this is an rvalue reference because there's no type deduction taking place here, because the type of the vector will be specified by the user, and when they specify the type of the vector, that also specifies the type of pushback's parameter. If we contrast pushback, now remember, this is vector. Everybody knows this class. If we contrast pushback with inplaceback, how many people are familiar with inplaceback? Okay, inplaceback, added for C++ 11, it's a lovely function. With pushback, if I go back one slide, with pushback, if I have a vector of widget, I push a widget into it. The problem is, sometimes you don't have a widget to push. Sometimes what you have are constructor arguments to create a widget. Now what you could do is you could create the widget, that would cost you a construction. You could then call pushback, and the widget would then be copied into the vector or moved into the vector. Either way, that's a second construction. And then the object you created to push back would be destroyed. But if all you want to do is get something into the vector, what you really would like to be able to do is to say, here are a bunch of constructor arguments, create the object directly in the vector. That is what inplaceback lets you do. So here's inplaceback. Inplaceback takes 0 or more arguments of arbitrary type. So the ... means 0 or more arguments. Now, this could be a vector of widget, this could be a vector of string, this could be a vector of vacation islands. We don't know what it's a vector of. Because we don't know what it's a vector of, we have no way to predict what the number or type of constructor arguments is. So this takes an arbitrary number of objects of arbitrary type. Now in this case, the name of the type parameter is args. This is a variadic template. If you've never seen variadic templates before, just ignore the ... and treat it as if it took one parameter, and just remember it means it can have 0 or more. Args will be a deduced type. If somebody passes me an int, this will be int. If somebody passes me a string, this will be string. If somebody passes me a set of double, this will be set of double. It's a deduced type. And look, it has the proper form, type ref. This is a universal reference. It does have type deduction. It has the proper form. So if I call inplaceback with 10.5 here, the compiler will deduce the type here to be double, because this is an rvalue. Remember, all numeric literals are rvalues. Because this is an rvalue, this will become an rvalue reference, and we will end up, the parameter type will be double ref. So this is a universal reference. And if I go back one slide, this is not a universal reference. even though they're both member functions inside the vector class. It's because in one case we get type deduction and in one case we do not. It is interesting to note that in the vector class, there are two versions of pushback. One of them is for copying lvalues, one of them is for moving rvalues. But there's only one version of emplaceback. This is very common. A universal reference accepts lvalues and rvalues. There's no reason to overload. It already accepts everything. But because this is an r-value reference, it will typically be paired with an overloaded version taking an l-value reference. Generally speaking, you will overload with r-value references. You will not overload with universal references. Because a universal reference already does everything an l-value and r-value overload can do. What emplaceback is going to do, emplaceback takes a bunch of arguments, it doesn't even look at them. It takes the arguments and immediately hands them off to the constructor to create the object inside the vector. All it does is take the arguments and give them to somebody else. It simply forwards everything. What emplaceback does motivates the term forwarding reference. Most functions that take universal references, all they do is accept them by reference and give them to somebody else. Syntactically speaking, a universal reference has to be type ref where the type is entirely deduced, completely deduced. So, that's a universal reference. We have type deduction, the type is completely deduced. This one here, notice I declared a const tref. That const will not be deduced. As a result, this is not a universal reference. This is actually an r-value reference to const. Someone asked me during one of the breaks whether there are any uses of r-value reference to const. The answer is yes, but they are very, very, very uncommon. The only use I know of an r-value reference to const is when you want to overload so that r-values will not be accepted, in which case you delete the function. I do not know of any uses where you actually, at runtime, accept an r-value reference to const. R-value reference means candidate for moving. Const means can't modify. These two things are contradictory. Vector of t ref. T will be deduced, but vector will not be deduced. This is an r-value reference. This is not a universal reference. If W is a widget and I say auto-ref, the type auto-ref is completely deduced. As a result, this is a universal reference. V1 is an L-value reference to W. Const auto-ref, which you should now realize means something completely meaningless. This is going to be a const R-value reference. And this line will not compile because this is an R-value reference and we're attempting to initialize it with an L-value. So that line will not compile. Yeah.
So I got a question. So if we don't see the value where we declare and initialize a widget object, then it's universal reference, but we know that it's L right now. So it's not universal ref at that moment. It just uses the same syntax.
This one here, you mean?
Yeah, yeah. This in and of itself is a universal reference. Yes.
But you're right. The minute we look over here to see how it's initialized, we can tell immediately what it's going to become. That's actually not any different from this. This is a universal reference. The minute we see how call, when we see a call to it, at that point we know whether it's an lvalue reference or an rvalue reference. But if all we know is trefref, at that point all we can say is it's one or the other. As I said, the most common situation is you're dealing with a template parameter. That's usually the situation. Because as you point out, with auto-ref, first, it's uncommon to type this anyway. And secondly, you can see right away how it's initialized. In C++ 14, when you have auto-ref parameters to a lambda, you'll be in the same situation. You'll see auto-ref in the parameter list, but you won't know whether it's an lvalue or an rvalue reference until you see the call. Does that help?
Yeah. Can you, one thing is that, yes, do I understand it correctly that defense implement a single pushback function that will forward the reference to the appropriate constructor because there is no way to make a universal reference of a known type?
Okay, so the question the question essentially is, why can't we write a function taking a universal reference for pushback,
Yes.
but restrict that type so it is always of a vector of t, so it's always of type t? You can write such a function for what I mean. It is possible to write that code. It would not be easier than simply overloading these two here. The universal reference itself, you are correct. The universal reference itself has to accept everything. So that part, you have to accept everything. What you can do is inside the function, you can then use something like a static assertion to cause the code to not compile if it weren't the same as the type of t. So you could actually say, I'll accept everything. And then inside the function go, but I'm going to not compile if it's not the type that I expect. So you could write that function, but this is the conventional way to express that I will accept either either L values or R values of a specific type. All right, so I've told you it has to have the right syntactic form. I've told you the type has to be completely deduced. So the question is, how much flexibility do we have in declaring a universal reference? Well, you can choose whatever parameter name you want, and you can put white space almost any place you like. And that's it. So if you want to call it param type, you can call it param type. If you want to put a space around the two ampersands, you can do that. If you want to put a space in front or a space after, you can do that. That's it. Everything else is completely dictated by the language. So practically speaking, the only choice you have is what is the parameter name you're going to use. After that, it's going to be that name, ref. Otherwise, it's not a universal reference. So the guideline is to distinguish universal references from R-value references, which is nice. Now, I hope we can at least tell them apart. But I haven't motivated why you care. Why did I introduce this terminology? Well, the next guideline gives you some idea. You should pass and return R-value references with move, and you should pass and return universal references with forward. So now we're beginning to understand when you use move and when you use forward. This is the situation. An R-value reference is definitely bound to an object that may be moved. So here is the widget move constructor, and I know that RHS, I know for sure it's bound to an object which I can move from. It has to be. On the other hand, a universal reference might be bound to an object that could be moved. So here's a setter, and it says I'll take either an L value or an R value for setting. Now, because I don't know whether I'm going to get an L value or an R value, I don't know whether I can move from it. If I get an L value, I have to copy. If I get an R value, I can do a move. The fundamental difference between rvalue reference and universal reference is rvalue reference, you know, is bound to something that can be moved from. Universal reference, you might be bound to something that can be moved from. That is the fundamental difference. I have already explained this. It is worth reminding you. Parameters are L-values. All parameters are L-values. If I have an int, I can have an L-value int, like the variable x. I can have an R-value int, like the number 22. If I just tell you I have an int, that does not tell you whether it is an L-value or an R-value. L-valueness and R-valueness are independent of type. Every type can have L-value instances of the type and R-value instances of the type. I can have L-value ints, R-value ints. I can have L-value pointers to ints. I can have R-value pointers to ints. This parameter is an L-value because it has a name. Its type is R-value reference. If I have a type that's R-value reference, I can have L values of type R-value reference. I can have R values of type R-value reference. Most people find this initially confusing. How can you have an R-value reference that is an L value? But it's easy. It's because the two concepts are completely independent. This is an R-value reference. RHS, however, is an L value because all parameters are L values. They have names. You can take their address. This is a universal reference, but the parameter, new name, is an L value. It has a name. You can take its address. Parameters are always L values. The whole motivation behind move semantics in C++ 11, the major feature in C++ 11, is to make it possible for R values to be moved from. Which means that if I call a function and I pass it some argument, it is important that this function have the opportunity to treat L value arguments and R value arguments differently. It should be able to do that. Which means if you have an R value reference and that R value reference gets passed to another function. Now remember, the R value reference is definitely bound to an R value. But the parameter of type R value reference is an L value. Which means when you pass that parameter to another function, you need to cast it back to be an R value so that the function you're calling will receive it as an R value. So here's my widget move constructor. So in this case here, here's widget, and widget, this is its move constructor. It has a name, and it has, in this case, a shared pointer to some data structure. So what I want to say is, my name is the name of the right-hand side cast to an R value, and my shared pointer is the shared pointer of the right-hand side cast to an R value. Notice, the parameter is an R value reference. I use move on it everywhere. Why? Because I'm giving the opportunity, in this case, this is going to call a string constructor, this is going to call a shared pointer constructor. Those constructors need to have the opportunity to treat it like an R value. If I did not include the word move, these things here would be L values, and I would always copy things. I would never move them. Yeah.
In this case, you call move on all those individual members of the argument, not on the argument itself.
Okay, that's a good point. So in this case here, I'm not calling move on the actual parameter. I'm calling move on a field of the But this parameter is an L value, which means its data members are also L values. So with another string. So I have to do it on a field-by-field basis, but you are correct that I'm not applying move to the entire parameter in this case. What I'm doing is I'm applying it to parts of the parameter.
So you partially move basically parts of that RHS over.
This,
not move the whole thing.
this line here will, this particular line here will move one field of it. And this line here will move the second field of it. And you're right. This by itself is a partial move. This by itself is a partial move. On the other hand, if you ask yourself, how can I actually move an entire object? You move it field by field. And what is the function that defines what it means to move it field by field? It is the move constructor. So other functions will typically cast the whole parameter, but for the move constructor only and the move assignment operator, you will typically do it field by field. Yeah.
What happens if we pass Lvalue, the parameter, to widget constructor? Won't it screw up all the fields?
Okay, do you mean for this function here? You're talking about calling this function here?
Yes.
Okay, so your question is, let's suppose we try to pass an Lvalue widget to this constructor. And your question is, won't it mess up the widget? And the answer is, it would mess up the widget if that call would compile. But because this is an rvalue reference parameter, we can only bind to rvalues. This parameter cannot be called with an Lvalue, and if you try, the code will be rejected.
Well, what he probably meant is moving it. So if you have an Lvalue reference and pass it into the constructor with move,
let us assume that this is the only constructor that we've declared. This is the only constructor that exists. Let's just assume that. So, widget W1, W1 is an Lvalue. If I now try to call the widget constructor from W1, that's the only constructor that exists. As I said, this line will not compile, because this is an Lvalue and it can't bind. Now, let us suppose you say,
The first line will compile.
Well, that and the default constructor or widget. You said that it's the only constructor.
I love to deal with C++ programmers because if there's so much as a semicolon missing, parsing stops. No, fair is fair. Okay. So, this calls the default constructor. There's still some stuff we'd have to do to make it fully compiled. Trust me, for purposes of this example. This will not compile under the assumption that these are the only two constructors we have. Let us suppose, however, you say, okay, this won't compile. I will make it compile. Okay. This is an R value. Remember, that's what move does. It casts it to be an R value. So you can't say, I'm now passing it an L value. You're not passing an L value. You are passing an R value. So there's purely from a language point of view, from the point of view of a C++ language person, you are passing an R value, you're not passing an L value. Now, from the point of view of a programmer, which is really the motivation for your question, from the point of view of a programmer, what you're saying here is, I give you permission to move from W1. That's what using move does. It doesn't actually say do a move, it really says I give you permission to move. So, to get to the original question, it is never so close to being true. You cannot pass an L value to this function. The only way a named variable could get passed in and have its value change, the only way would be if somebody expressly cast it to be an R value, in which case they should not be surprised if its value changes. Does that address your question?
Yes.
Okay. One of the nice things about C++ is that you can say, this is almost completely true, and it's true enough to be remembered. You can't get an L value, you can't get an R value by accident. So if I have a named variable, if it's going to be treated as an R value, it's because I applied move to it. There's a couple of obscure exceptions, but that's basically true. Yeah.
The compiler sees that the W1 is not used anymore. Is it allowed to do optimization and call constructor instead?
Okay, so the question is, let's suppose the compiler notices that I've got this L value. Let's suppose the compiler notices I've got this L value. It's never used again in the function. So even though there's a copy operation that should be performed, the question is the compiler able to say, I'm going to sneak in a move? Because it's never used again. And the answer is no. In general, the compiler cannot transform copies into moves. And one of the reasons for that is because it's not true that it's never used again. Its destructor would be called. And the destructor could behave differently depending on whether it had been copied or moved from. So, as a general rule, compilers are not permitted to take L values and treat them as R values. There's a couple of obscure exceptions, but as a general rule, L values must be treated like L values, R values must be treated like R values. But big point here is, R value references imply you want to use move on them. Now, standard for, we've already talked about, it conditionally casts to an R value. So in this case here, when somebody passes in new name to my setting function, universal reference, it has the right syntax, it's a template, we have pipe deduction. Now, new name might be bound to an L value, but it might be bound to an R value. As a result, we don't want to call move. Calling move would be horrible. We want to apply forward. That's what forward is designed for. We saw the conceptual implementation of forward earlier. What it does is it will cast this into an R value only if it was bound to an R value when it was called. It's a perfect fit. If you have a universal reference, it might be bound to an R value. Forward conditionally casts to an R value. They're made for each other. And the question came up earlier, all right, let's suppose I just did a move. So if I get a universal reference parameter and I apply move to it, this code will compile. This is an unconditional cast to an R value. This is the slide we actually saw earlier. The problem is at the call site, and this is your concern. At the call site, I have a widget. I now get a widget name, which is a string, and now I call the setName function with the widget name. Widget name is an L value. I do not expect its value to be changed when I call setName. Now, setName takes a universal reference. The convention is universal references copy lvalues and move rvalues. That's what they're for. So the caller has every right to expect that when they call setName with an lvalue, the lvalue is not modified. Now you're right, there's no const here. But remember, for an rvalue, const would be wrong. But if we used move here, the lvalue here would get bound to this reference. This reference would then be turned into an rvalue and passed to the assignment operator for string, and I can assure you that the assignment operator for string will in fact reach over and grab the contents of its memory. Which means when we're done, WName at the call site has had its value changed. That will probably break calling code. This is what we want to prevent. And this is a bug in the code that will, this is just wrong. This is not a matter of style. This is wrong. It'll compile, but it's still wrong. Yeah.
What are the uses for STD move? When do you actually use it? If it's not so safe.
Okay, so the question is, when do you use std move? You use std move if you receive a parameter, excuse me, if you're in a function and the declared parameter type is rvalue reference, so you know you have an rvalue, and you pass it to another function. So if you have an rvalue reference parameter, you know you're bound to an object that can be moved from, so when you give that parameter to somebody else, you will apply move to it. Make sense?
But why compilers cannot detect that we are doing this wrong move?
I'm sorry?
Why compilers cannot detect that we are doing this move
Okay,
instead
so the
of
question is,
forward?
why can't compilers detect that we're doing the move? Because move is a cast. Compilers never know if a cast is correct. Remember, move is just a fancy name for a cast. That's why. Because they have no idea whether it's right.
Why not simply always use forward?
Okay, so the question is, why not simply always use forward?
Yeah.
There's two reasons, and the more important of the two reasons is because they express different things. Move says unconditionally cast to an rvalue, and the reason it's called move is because it typically sets up a move. Forward says conditionally cast to an rvalue, and it typically doesn't set up a move, it sets up a forwarding operation to some other function. So that's the high-level conceptual reason, is we're trying to express different things. From a mechanical point of view, in terms of actually writing the code, you could express everything in terms of forward. You don't need both. You don't need move at all, you can use forward. Although I'd like to point out, if you don't want to use move because you've got forward, you can get rid of both of them and just write the casts. Remember, all they're doing is casting. Notice that with forward, you have to specify the type. With move, you do not have to specify the type. So forward, in addition to being order type, has another possible failure mode if you pass the wrong type here. And there are obscure situations where you can actually pass the wrong type. So with move, that possible error is eliminated. Make sense? Yeah.
Don't you need to use move when you want to move some, for example, a local variable, and you know that you won't use it anymore?
Right.
Using a forward would copy instead of moving.
Okay, so the comment is, let's suppose I have a local variable. I know I'm done using it, so it can now safely be moved from. And so, your comment, I mean, this is an example of that here. So, I'm done using W1, I now want to give permission to use it. Now, your comment was, if I used forward, it would be copied because it would be passed in as an lvalue. But that's not necessarily true. If I said, if I call some function f, whatever it happens to be, and now I say standard forward, W1, and that's basically what the forward call looks like. But remember, with forward, you have to specify a template argument. And determine whether it's copied or moved. Because remember, that type will encode whether it's an L value or an R value. So using forward on an L value does not guarantee it will be treated like an L value. It depends on what you pass in here. Now, we could spend a lot of time talking about the weird things that could happen. Let me tell you about C++ programming. This is the design space of some feature in C++. Perfect forwarding, R-value references, lambda functions, shared pointer, it doesn't matter. That's the design space. I'm trying to explain to you about the design space. Naturally, what I want to do is I want to talk about the sweet spot in the middle where everything works perfectly, where there's no surprises, where it delivers lots of value, it's easy to read, it's very efficient. And whenever I teach a class like this, nobody wants to talk about this. Everybody wants to know, well, what happens right here? Or what would happen right here? Or what if you do this, and you do this, and you do this, and that simultaneously, which no one would ever do, but what would happen? I can answer these questions, but I can't do it in the limited amount of time. I will be happy to hang around afterwards, but we need to try to focus not so much on what would happen if we did the following 16 wrong things. They all have answers. But instead, we need to focus more on what are the right things to do and why are they the right things to do. I love C++ programmers. So what I've told you so far is, if you have a universal reference, apply forward to it. If you have an R-value reference, apply move to it. And that's almost true. But it's not completely true. Let us suppose I have this function set sign text. It takes a universal reference. So because it takes a universal reference, I should be thinking, I have to apply forward to it. However, what I'm going to do here is I'm going to set the text of the sign with whatever the text for the sign is. And then I'm going to then I'm going to add to the history of the sign the text that we put on there. So I change the text on the sign and then I log that in the history. Now, this is a universal reference, which means maybe somebody passed me an R value. If somebody passed me an R value, it means I can move from it. That's great. The problem is, if I move from it here, if set text does a move, I can't add it to the sign history. If I let set text take the value, I can't put the value in the sign history because it's gone. So what I need to do is, here, I want to have the text to be copied. I want it to be treated like an L value. The only place I want to apply forward to it is the last time I use it. So in this case, I don't apply forward to it here, but I do apply forward to it here. And the reason I'm doing that is because at this point in the code, I don't want it to be changed. I want it to be treated like an L value. Now remember, L values are things that can be accessed from multiple points in the source code. And that's exactly what I'm doing here. I'm accessing it here, and I'm also accessing it here. And I don't want it to be changed here because I need to use it again here. So the real rule is use move on the last occurrence of an R value reference, and use forward on the last occurrence of a universal reference. Most of the time, in most of the functions that you write, there's only going to be one use. But if you find yourself writing a function such as this, where you need to use the parameter more than once, you want to make sure that its value is not changed too soon. Yeah.
Or you pass constructor.
What's that?
Or you pass a constructor. Don't use universal reference.
Okay, so the comment was where you pass by const reference. It's important to understand that we're looking at things from, there's two different sides of the interface. As somebody declaring a function, I can pass it by reference to const. But as somebody calling a function, all I can do is pass the argument. So when I'm looking at, for example, this here, I can't change the way set text was declared. Maybe it takes it by reference to const, but maybe it doesn't. I can't change that. So from the point of view of a caller, from a caller's perspective, my only choice is I either apply forward or I don't. And you're right, if I was designing the interface, I might design a different interface, but in this case, I'm the caller, not the function implementer. So if you have multiple uses of an rvalue reference, you will use move on the last one. If you have multiple uses of a universal reference, you will use forward on the last one. The rule applies to return types as well. Let us suppose I have a function for adding matrices together. So here's operator plus for a matrix. Notice that this is an rvalue reference. This is a temporary matrix. That means I can safely change its value and I don't have to worry about somebody else being affected. This is another matrix which is a const reference. So this one is interesting. This one I can reuse its storage if I want to. What I'm going to do here is return a brand new matrix, the sum of the two matrices. So what I do is, the temporary matrix, I say temp plus equals y. Notice that this temp here, it is definitely bound to an rvalue, so I can do with it whatever I want to. And now what I want to say is, I want the contents of this matrix to be moved into the return value. By the way, this has nothing to do with the return value optimization. The return value optimization does not work on reference parameters. This is a completely different thing. And so, if I just said return temp, temp has a name, temp is an lvalue, which would mean the compiler would be required to copy temp into this location here. Now somebody asked earlier, can't the compiler change one to the other? And the answer is no. In general, the compiler is not permitted to take this lvalue and treat it like an rvalue. Not when we're talking about a parameter that's passed in by reference. So, if I go back one slide, by applying move to it, I tell the compiler, treat this as if it were an rvalue. Now, the details are not important. The general rule is important. What's the general rule? rvalue reference, apply move to it the last time you use it. It's completely consistent with what I told you before. And in fact, if you get an rvalue reference and you don't apply move to it, you're violating the rule that I was telling you about. But now I'm explaining why the rule applies to return values as well. If I have a function called reduce and copy, I take a fraction, I invoke the reduce function on it to reduce it down to its reduced form. If the new fraction is returned by value here, notice, universal reference. So I apply forward the last time I use it. If we didn't have the forward, this would be copied into the return value. With using forward, it can be moved into the return value. The rule is completely consistent. If you have a universal reference, the last time you use it, you want to apply forward. If you have an rvalue reference, the last time you use it, you want to apply move. These are not optimizations compilers can perform in general. Yeah.
Shouldn't the return type also be rvalue?
So the question is, should the return type also be an rvalue reference? Are you asking?
Yeah.
As a general rule, having functions return references can lead to the possibility of dangling references. For example,
Yeah, okay.
in this particular case here, for example, this could be an rvalue. We don't know, but this could be an rvalue. If it's an rvalue, whatever it refers to will probably be destroyed at the end of the statement. So if this came in as a temporary object and we returned a reference to it, we would be returning a reference to an object that was going to die at the end of the statement. So as a general rule, you do not want to return references. There are some exceptions, obviously. The array bracket operator for vector returns references, but that's because it knows that its storage will continue to exist for a while. You have a question?
So my understanding basically is that it first modifies the variable that can be passed in by reference and then returns copy.
Correct. Correct. So what I'm assuming happens here is that this reduces the original fraction, and then it returns a copy of the reduced fraction. It's kind of a funny function, but that's what it is. Okay, so at this point, you're probably thinking, this is great. If I apply move and I apply forward, it helps compilers optimize their return values. This is so wrong. So wrong. Let me remind you that what we've just seen are examples involving rvalue reference parameters or universal reference parameters. That's what we just saw. So, let's suppose, here's my function f1, it returns a widget by value. I declare a local widget w, and I say return w. Now, this, at first glance, this can look to you like a copy. You declare a local variable, this is an lvalue. So it looks like, oh, we're going to copy this into the return value location. This looks expensive, because I got to copy it. You might be tempted to help your compiler. You might be tempted to say, you know what I'm going to do? I'm going to turn it into an rvalue like this. Such a bad idea. The reason it's a bad idea is because there's a special rule in C++. The special rule says, if you have a function with a local variable, and the type of the local variable is the same as the return type of the function, then compilers are permitted to take this object and actually construct it in the return value location so that it never has to be moved or copied there. This is what is known, do I have it here? No, as copy elision. And in case you would like to know where to find it in the standard, section 12, subpoint 8, paragraph 31 and 32. I'm not kidding. But the wording of paragraph 31 and 32 is very specific. The wording says, if you have a local variable of the same type as the function's return type, and you return that local variable, then you can put the two of them in the same chunk of memory. If you have a local variable of the same type as the function's return value, and that's what you return. See this return statement? This is not returning a local variable. Now, you and I know what move does. Compilers are mind-numbingly stupid. Move is a function, right? It's a function. Now, we know what it does, compilers don't. The compiler goes, wait a minute, this is returning the result of a function call. The result of a function call does not qualify for copy elision, which means this actually will move things into the return value location. Now, a move doesn't sound so bad until you realize that for this code here, there was no move or copy. The code is more efficient without the move. But notice, you're trying to use move here on a non-rvalue reference. There are some occasions, as we talked about, where if you're really done using a variable, you can apply move to it because you're really done using the variable. That does sometimes make sense. But a return statement of a function that is returning by value is not one of them. This actually generates worse code, better code. I saw a presentation one time at a conference. The title of the talk was, "Please Don't Help Your Compiler." And this was one of the examples they talked about. Okay.
Constructor won't be called. It's copied the result.
Which example? This one or this one?
The first one, F1.
The first one. Okay. The comment is that the destructor won't be called. So let's be clear here. Every constructor will be matched by exactly one destructor. So what will happen is this object here will be constructed in the return value memory for this function, and that return value will eventually be destroyed. So this object will have a destructor call. It's just that it won't occur at the end of this function. It will occur at the end of the statement calling this function.
Yeah, but if it would copy this value to result, then the constructor and destructor would be called twice.
If it actually did a copy, then we get one constructor call here.
Yeah.
We get a second constructor call up here.
Yeah.
We would then have a destructor here to match this constructor.
Yeah.
And this object here would have a destructor to match it. So again, the number of constructors and destructors would match.
Yeah, but if we have a static variable that increases every time in the destructor, then because of this optimization, the code will not work as expected.
One of the rules from C++, in fact, you've been sitting too long and it's right after lunch, everybody has big heavy food in their bellies. We'll take a 10-minute break right now. We'll come back, we'll talk about that. So we'll take a 10-minute break.